Our speaker for today is Professor Paul J. Dauenhauer. Professor Dauenhauer is a distinguished McKnight University professor at the University of Minnesota and the Zolt Rumi Innovation Chair and MacArthur Fellow in the Department of Chemical Engineering and Material Science. He's the director of the Center for Programmable Energy Catalysis, a U.S. Department of Energy Frontier Research Center. His work has been highlighted with the NSF Career Award, the DOE Early Career Award, the Camille Dreyfus Teacher Scholar Award, and the AICHE CRA Young Investigator Award. He has co-founded 3 companies, and his patents serve as the scientific foundation of 5 startup companies, including Syronix Renewables, Lacryl Technologies, Carba, Activated Research Company, and Enverde LCC. Thank you, Professor Dauenhauer, for joining us. The stage is all yours now.
Okay, thank you everybody for the invitation to speak with you today. I'm speaking to you, hold on, let me hide that. I'm speaking to you as the director of the Center for Programmable Energy Catalysis, and I'd like to tell you today about this concept we're developing called Programmable Chemistry and Catalysis. Let me tell you first about the University of Minnesota. The University of Minnesota is located in Minneapolis. We are a top 5 program in chemical engineering for the past 4 decades. We're over 40 faculty working in this area of sustainable materials, catalysis, polymers, and many more fields, including bioengineering. The location is absolutely fantastic. Minneapolis, if you look it up, is a wonderful place to live for quality of life, affordability, and activity. We're one of the largest universities in the United States with premier facilities, multiple programs, and multiple opportunities for students, both for education and for developing your career. So please consider us in the future. What I'd like to talk about at the beginning here is the field of catalysis. And for the past 100 years, our thinking about catalysis has been very effective. And that is this thinking of structure and function. If we find the right structure, we will obtain the best catalytic performance. And I showed this picture here of a bridge because that is exactly what you think of when you see a bridge. That structure gives you a particular function, in that case, the ability to drive across it. But if we think of materials, in the past 20 to 30 years, the expansion of synthetic techniques in nanomaterials in particular has given the catalysis field immense opportunity to create new active sites that can control chemistry. And it's been a very exciting time to be a catalysis researcher because we have all of these new microporous materials and nanostructured materials to improve catalytic chemistry, and it's made a huge impact. What I want to talk about, though, is this idea that we could take these advanced techniques and use that for energy applications. So in the past 10 years, wind and solar has gone from something very expensive to something incredibly cost effective. It even beats conventional approaches of generating power. But a lot of times it's located in places that are not highly dense in people. So we have to move power around, we have to store it. And one way to do that is to convert renewable electrical power to chemical energy by converting things like water, CO2, and air to molecules like hydrogen, ammonia, and methanol. And this is where the catalysis challenge comes in. Almost all of these reactions are what we call Sabatier limited, or limited by the Sabatier principle. And you can see that all of them exhibit, if we plot the reaction rate, the turnover frequency, which is the vertical axis that you see here, as a function of a descriptor of the catalyst, they all exhibit this maximum value in the catalytic activity you can see. So if you look, for example, on the top right, that's the ammonia synthesis reaction, and the best materials are osmium, ruthenium, and iron. If you look in the bottom left down here, you can see that the best materials are copper. If you look at the oxygen evolution reaction, which is important for making hydrogen by electrolysis, the best materials are things like iridium oxide. And this is a problem for many reasons. Number one, we would like to go faster. And a lot of times we're limited by the materials that are at the peak of these volcanoes, so the Sabatier volcano, which are something like iridium, which is very expensive and not available in large supply. Now, where does this come from, and how can we disrupt this approach to catalysis? So the premise of modern catalysis of structure function comes from this idea that the energies on a surface are related to the composition and structure of that surface, which makes a lot of sense. If we think about a reaction, this is a generic reaction that you see here. To go from the reactant to the product requires this large barrier if it's uncatalyzed. And so we adsorb a molecule to a surface, lower the barrier. So the green barrier is smaller than the blue barrier here. And that gives you the benefit of the reaction surface itself to speed up the reaction. Now, if you wanted to make a better catalyst, you could potentially find something with a different energy surface, a different material, and that would lower the barrier of desorption. Now these two energies are about the same. Well, if you wanted to go even faster, you could try to find another material that might do something like this. When you make the surface reaction more exothermic, you're going to pull down this energy barrier and make the reaction go faster. But the problem is when you do that, you make the desorption barrier larger. And this is a very simple cartoonish explanation of the trade-offs that exist in designing catalysts. If you speed up one step, at some point you'll slow down another. So we can think of the Sabatier limit as kind of this balance between the rates of different competing steps in a catalytic reaction, and that peak, that maximum value, is kind of the best balance of all particular reactions. So where does this come from? Well, this comes from this idea that there are periodic trends in materials. So if you think of two different metals and you think of a molecule binding to those surfaces, they bind with different energies. So carbon monoxide, for example, binds to this metal more weakly than it would bind to this metal, metal number 2 right here. And if you think about breaking the carbon-oxygen bond, it'll form carbon and oxygen atoms on the surface. Those also bind with different energies. But those are predictable based on the metals themselves. So while you see that the amount that they change in energy is different, those scale by what we call a linear scaling relationship, which is predictable by two parameters, a slope and an offset. And you can see here the activation energy is different as well. This one's an uphill reaction, this one's a downhill reaction. What I'd like to do instead, though, is I'd like to take one material and I'd like to be able to change its properties. So let's say I take one metal and I have it in state 1, then I perturb it in some way to get state 2, and then I perturb it again to get it into state 3. And as I'm doing that, that same material, I'm changing the activation energy of the reaction. So in this state, this electronic state, it's uphill. In this electronic state, it's about thermoneutral. And in this state, it's exothermic. These could also be predicted by linear scaling relationships. Now, the question, though, is how do you do something like this? How do I make one material take on different electronic states such that I can change its catalytic properties? So this is something we've been thinking about for a very long time. If we think about what chemistry is about electronic interactions. So if I could electronically dope a surface, I could change its catalytic properties. Now, how do you get enough electrons into a material or pull enough electrons out of a material requires a mechanism to stabilize charge in a surface. And the best way to do that is to provide a countercharge. So what we've developed is this concept you see over here on the left. We call it a catalytic condenser because we're condensing charge in the active sites. Well, what we do is we take our conductive support, in this case silicon. On top of that, we grow an insulating layer. And on top of that, we put our active surface supported on graphene, which is an electron conductor. And when we do this and we apply a voltage between the top and the bottom, we can actually stabilize a large amount of charge in the active surface, thus changing its catalytic properties. In this case, I'm using alumina because alumina is an acid catalyst. And if I pull electrons out, I put holes in, and that makes it even more acidic. And that's what I would like to do, tune the acidity of alumina by applying a voltage. So here is the device. You can see a photograph of it here in the bottom left. The top left is a 3D cartoon of that surface. We put down the graphene first on top of the hafnia. The hafnia is the insulating layer. And on top of that, we put a very thin layer, just 2 nanometers of amorphous alumina. On that TEM on the right, you can actually see where the graphene is, and then you can see the alumina. In the green here, you can actually see the alumina layer. And you can actually see a thin carbon layer there in bright red. So if I think about these materials now, if I make a tunable material, I can compare this to different materials themselves. And one way to do this is to study how they react molecules on their surface. So we can take a very well-studied reaction, isopropanol dehydration. So isopropanol dehydrates to make propene and water. And if I put these on a surface and ramp the temperature with time, each material will exhibit a reaction at a different temperature. So tungsten oxide reacts at a lower temperature than gamma alumina, which reacts at a lower temperature than titania, and zirconia is the slowest reaction. It requires a very high temperature to react. But if I think of our material, we could start with alumina. So we'd start right here. And then if we were to remove electrons from its surface, we would make it more acidic. And so we would slide to the left on this diagram. And rather than the discrete materials that you see in the top, we would continuum of possible materials that are tunable depending on what voltage I apply. So the question is, well, how many electrons can I pull out of a surface? Well, that depends on the properties of the material itself. In this case, the hafnia is the determining factor in that, and the voltage I apply. So what you can see here, this is some measurements we made of two different devices. One is the base device with just graphene in blue, and then the device that has alumina on graphene, which is our active site for catalysis. And as you can see is that I pull a lot more electrons out when I have alumina there than with graphene. And as I apply more voltage, I pull more electrons out. And so what I'm actually doing now, if you look at this, is I'm pulling out almost 10 to the 13 electrons per square centimeter. And I have somewhere about 10 to the 13 to 10 to the 14 active sites. So we're pulling out, on average, about 10% of an electron per active site, which is a lot. Now, what happens when we do that? So this is the actual experiment where we take isopropanol, adsorb it to a surface, and then slowly ramp the temperature linearly and measure the peak at which it reacts to form propene. So these are the propene peaks over here on the left. And you can see that when I apply a voltage of 0, the surface just behaves like alumina. And then as I increase the voltage from +1 to +2 to +3, the peak of propene formation shifts to lower and lower temperatures, indicating that it's a better acidic catalyst. So you can see here then if I take those peaks and I measure enough of these, I can get statistics to show that I'm decreasing the activation energy by applying a voltage and removing the electrons from that surface. So that was what we did experimentally. My colleague, Matt Newrock, at the University of Minnesota, was able to calculate this exact system by taking a defect site in alumina and then comparing both a neutral system on the right in that diagram and on the left where he's pulled out a little more than 10% of an electron per active site. And his calculation matches very closely with what we observed experimentally. So when you pull out about 12.5% of an electron per site, you decrease the barrier by about 0.25 electron volts, which is very close to what we measured experimentally. So let's back up and just summarize kind of what we're doing here. If we look at the reaction we were talking about, isopropanol dehydration here, you can see that if we were to ramp the temperature of the surface, we would see peaks for different materials, like alumina in blue, titania in green, and zirconia in brown. But if we take alumina and we remove electrons from it, it's like creating a new material. So we joke that we call this electronic alchemy. We're changing the properties of the material such that it behaves like a completely new material itself. It exists as a unique peak. Now, what we're doing here is we're just manipulating the Fermi level, which is changing the electronic properties of the active site itself. And this is essentially a platform device. There's nothing inherently special about alumina. In fact, it's an insulator. We could look at other materials that are also active sites, so other metal oxides, other metals, metal carbides, and we have the ability to potentially manipulate the electronic properties of those sites as well. And so what we did very early on is say, well, we've looked at oxides. Let's look at nanoclusters, which are of metals, which are very common active sites for a lot of catalysis. So in this case, we have the same design of the material. You can see here, we're going to have hafnia, and we apply a potential bias to this. We end up with electrons in the top and holes in the bottom, and those stabilize each other. We have our graphene layer to move charge from left to right. And then we put our nanoclusters of platinum on top of that. So you can see here at TEM on the right, you can see the 70 nanometers of hafnia. You can see a very thin layer of carbon, and then the little clusters of platinum on top of that. Now, what we can do here is, instead of doing the isopropanol reaction, I'm going to adsorb carbon monoxide, and I'm going to measure the temperature at which it desorbs from the surface. So you can see over here on the plot on the right, this is the mass spec of carbon monoxide desorbing from the surface as I linearly ramp the temperature. And so you can see here, carbon monoxide at 0 volts comes off somewhere in the middle between the negative and positive biases. So if I apply a negative bias of -3 or -6 volts, I'm weakening carbon monoxide binding and it comes off at lower temperature. If I apply a +3 or +6 volts, the carbon monoxide comes off at higher temperature, indicating stronger binding. I can take these peaks and I can back out then the binding energy shift of about 20 kilojoules per mole between -6 and +6 volts for this particular system. So again, I'm tuning the binding energy of molecules on a surface. Now that was a hafnia-based device. I can make devices that are potentially more powerful. And what I mean by more powerful is putting more electrons into the surface. And a way to do that is to change the hafnia for something like an ion gel, which is an ionic liquid polymer combination. And what you can see here now, I've made this, instead of on a silicon surface, I've put it on this polyimide surface, which is flexible. So I can actually bend it or curl it or coil it, whatever I want to do. And you can see here, I have a stability of about 200 degrees C over 48 hours with this material. But this has a significant advantage. Even though I have less thermal stability, I have considerably larger amount of electron density I can change in these active sites. And you can see this right here. So on the plot on the left, what I'm measuring again are the number of electrons that I've pulled out or added to a surface with charge. So here in in purple, you can actually see this is the device we were talking about before. You can see now we've increased by about 10x the number of electrons I can add to a surface or remove, depending on positive or negative voltage. And you can see over here now, on the plot on the right, I've significantly increased the number of electrons that I'm manipulating in that surface. I'm now up to about 10 to the 14 electrons per square centimeter, and my active site density is about 10 to the 15 for metals on this surface. So again, it's about 10% of an active site. Now, this has a profound effect on how molecules bind with the surface and react. So again, I'm doing the same experiment. If you look in the top left here, where I adsorb carbon monoxide onto platinum, and then I can change the electron density of those platinum clusters by manipulating the applied voltage. This time, though, I'm going to do a different experiment. I'm going to take this device you see right here, and I'm going to put it in this infrared spectroscopy cell. I'm going to bounce light off the surface and measure the surface coverage of carbon monoxide. So I can see carbon monoxide in the gas phase, and I can see it on the surface of this platinum device. And what I can do then is I can increase the temperature and measure the coverage of carbon monoxide on that surface. And what you see is what you would expect. As I increase the temperature from left to right here, the amount of carbon monoxide on the surface goes down. But if I apply different voltages, the temperature at which it transitions from high coverage of CO on the surface to low coverage shifts dramatically. So if I apply a negative voltage, I'm adding electrons to the platinum, I'm weakening the binding of CO, and it comes off at a lower temperature. If I pull electrons out, the carbon monoxide binds stronger, and I have to heat the surface up significantly higher to get the carbon monoxide off the surface. Now I can go for other types, architectures here that give me different performance. So I was using an ion gel, which is stable up to 200 degrees C. I would like something that gives me a lot of electron manipulation on a surface that I can take to even higher temperature. So this is a paper that was just published this past week in ACS Materials Letters, led by Dr. Kungro Oh and Amber Walton in my group, where they made these nanolaminate films of titania and alumina. And these films are very thin. They're about a nanometer each, and we repeat them over and over and over. You can see that here in the TEM on the right. You can actually see the different layers of titania and alumina. And that gives me a very powerful device with a high dielectric constant and high capacitance. Then I put these capping layers on, and I end up with a device that you can see down here on the left in this photograph. and I put metal clusters on it just like I have, so I have an active site. Okay, so what you can see over here on the left, this plot, if you haven't seen impedance spectroscopy before, it's a very simple idea. I can apply different frequencies of voltage, and then on the bottom axis here and on the vertical axis, I can measure the device capacitance. And what I want to know is, what is the maximum frequency I can go to before the capacitance starts to decrease? That's an indicator of the speed of the device. So in this case, I can go out to about 1,000 hertz. Now, what this means is that I can oscillate the potential of that surface over the entire surface about 1,000 times per second. So before we were talking about the ability to change a surface catalytic or binding energy properties, this tells me how fast I can do it. So 1,000 times a second, I could change how molecules bind to that surface. On the plot on the right are the 3 different materials I've presented so far. Hafnia, the ATO is this nanolaminate film I just showed you, and the ion gel. And you can see they fall in this straight line that indicates to me we're seeing the same behavior, just with different strength of electron removal. All right, so I have the ability now potentially to change how molecules interact with the surface electronically. I can change it significantly in binding strength, and I can do it very quickly, up to 1,000 hertz. Now, why would I want to do this is the question. There's a very specific reason, and that is I want to be able to manipulate the surface in a way that is favorable for the chemistry that I'm trying to optimize, either in rate selectivity or conversion in some way. So I need to think about what signal am I going to send to the catalyst surface to make it perform the way that I want in terms of its catalytic properties. And that's the idea of a programmable catalyst. I can send it a voltage signal that repeats for every catalytic turnover. That program is optimized to change such that the voltage changes to change the electronic properties of the catalyst in a way that's optimal for whatever I'm trying to achieve. So this is obviously a cartoon right here to get this idea across, but I have to put some thinking into it. I have to have a CPU equivalent that's saying, okay, I need to send these types of voltage signals to a surface to change the catalyst in a way that makes sense. So let me give you a very simple idea here of how this could work. Here's my device on the right, my catalytic condenser. And what I'm doing is I'm putting electrons in and I'm pulling them out. So when I pull the electrons out of the top surface, you can see the holes show up, and then I put the electrons back in. Now, if I think of a very simple reaction, A going to B, I can imagine essentially 3 things happening. A adsorbs to the surface, A reacts to B, and B desorbs from the surface. And those 3 steps, I can think of how would I want the catalyst to be for each of those 3 steps in particular. Well, really, I care about 2 of them. Where A turns to B, you can see that pink transition state flash up. I want it to bind very strongly. So that's why I have a positive charge under that condition. But then when I want to get the B off of the surface, I want to put the electrons back in and weaken the binding. And so a very simple program that I could imagine would be a sinusoidal voltage signal, where I'm increasing the binding energy and decreasing the binding energy, back and forth, back and forth. So this idea is actually where we started all of these ideas. If I think back to the start of the presentation, I was showing you this idea of Sabatier volcanoes. So here you can see the vertical axis is the reaction rate, the turnover frequency. And on the bottom here is some descriptor of my catalyst. And in this large black line here, you can actually see the Sabatier volcano. And the best material was right here in red. What we're proposing now is that I can move from left to right on this plot with these catalytic condensers. I can change the way molecules bind to the surface, which lets me move side to side. And the hypothesis originally was if I can move side to side on this plot fast enough, like you see here in purple, I could exist up here above the Sabatier peak. In fact, several orders of magnitude above, thousands of times faster than any catalyst that existed before. Now, this is the start of the hypothesis. What I want to show you and think about now is how should we think about catalysts that change with time theoretically, now that we kind of have a device in mind for how we could do it. So what's happening when I think about changing the electronic state of a catalyst? We think of a reaction as going between a reactant A and a product B, and then some energies on the surface in between. So here's A star and B star down on the surface with their transition states. Now, as I change the electronic state of a catalyst, I'm changing all of the energies, the energy of A star, the energy of B star, and the transition state energy. And what you think about is the energies of each species changed uniquely. So A changes only a little bit in this case, and B star changes a lot. So that's one of our scaling parameters I talked about earlier. But the effect is that it changes the transition state energy to go from A star to B star. You can see that the transition state energy in state 2 in brown is much larger than it is in state 1 in teal. And that's an opportunity to get from A star to B star in state 1 that doesn't exist in state 2. Now, people frequently ask me, well, we're talking about dynamics of catalysts. So what is programmable catalyst? Well, I consider programmable catalysis to be this box here in yellow. So there's two rows here. I can think of passive dynamics where things just spontaneously happen in a catalyst, like it deactivates. Or if I go to the middle column here, reactors might be unstable or processes might be unstable. In this case, we're talking about forced dynamics. We're forcing the catalyst to change with time. Now, there's many ways we can force processes, reactors, or catalysts to change. So a lot of times people say to me, well, is this the same thing as temperature dynamics of a reactor? That's this middle box here. And the answer is no, I'm not changing the entire reactor. We're just changing the catalyst itself. We're in the top left. And that's my definition of programmable catalysis. So let's explore this very simply. Let's take a very simple simulation. A is going to react to B. It can adsorb, it can react, and then it can desorb as B star. I'm going to put that in a reactor simulation, and I'm going to control the normal parameters I care about in a reactor simulation. The space velocity, which is like the residence time, how long it reacts, the temperature and the pressure. I'm going to define the catalytic chemistry, such as the overall thermodynamics, the heats of adsorption, the transition state energy. But now, because the catalyst is changing with time, I have to be able to determine how the catalyst is changing with time. So I have these new parameters. How much is it changing? That's the amplitude. Where does the catalyst start and end? That's just like, if you think of the condenser, that's the left voltage and the right voltage, the maximum and minimum voltage I apply. The frequency is how fast I change a catalyst. I said that before, it could go up to 1,000 hertz. And then the waveform type might be the shape it takes on. It might be a square wave, it might be a sinusoidal wave, it might be combinations of frequencies. So here's a very simple simulation. If you look at the top right, what I'm doing is I'm taking the catalyst and I'm flipping it between two states in a square wave. It's very strong binding, then it's very weak binding, then it's very strong binding, then it's very weak binding. And what you can see if you go down now to the bottom is that my surface coverage is changing a lot. So the molecules that are on the surface change between A being on the surface a lot and B being on the surface a lot, A being on the surface a lot, and B being on the surface a lot. And every time I flip, my reaction rate, which is the turnover frequency here in the middle plot, goes way up really quickly and then depletes the surface and comes back down. So I'm constantly filling the surface and unfilling the surface with A and B and making the reaction rate spike repeatedly for every oscillation. Now that's one frequency I've applied, but I can think of many frequencies. I could go very slow. So every 1,000 seconds here in green, I could change my surface. If I increase that to 0.25 hertz, I'm actually now at the Sabatier maximum. If I go faster though, as I go faster and faster and applying frequencies, my rate continues to go up. By 10 hertz, I'm over an order of magnitude above the Sabatier peak, and by 1,000 hertz, I'm 2 orders of magnitude above the Sabatier peak. So that's 4 frequencies. But what if I think of all the possible frequencies? So here's a plot of how I can think of the relationship between the frequencies I apply to the catalyst and the frequencies of reaction that I get out. So down here in the independent axis is the applied frequency all the way over 16 orders of magnitude. And the vertical axis is the reaction rate. And what you can see is that at very low frequencies, I have a very slow rate of reaction here in blue, below the red Sabatier peak. And then as I increase the applied frequency, I speed up, and I eventually pass the Sabatier peak, and I reach this maximum right here, at which point I can't go any faster. So I call that the resonance frequency. I'll say more about this in the next slide. At this point, I can't go any faster, and eventually my rate comes back down, back to the Sabatier peak right there. So at that resonance frequency is a very special case for frequencies that I apply. If I was to go left, I go slower, and if I go to the right, I'm less efficient. You can think of this very simply. I'm applying oscillations that don't speed up my rate at all, so it loses its efficiency. So people ask me all the time, can these systems be efficient? And what I wanted you to think about is if I'm applying a perturbation to a surface, let's say I'm oscillating the voltage, I'm changing the energy of that surface, and am I making molecules move in the direction that I want efficiently? So you can think of this picture right here of purple reacting to pink molecules. Every time I flip the surface in a catalyst state, all of the purple molecules are going to pink, right? And that's a very efficient system. And we've defined a quantity for this. We call it the turnover efficiency right here, which relates the dynamic turnover frequency to the oscillation frequency corrected by the average steady state turnover frequency. And the answer is these systems can be very efficient under certain conditions of amplitude and frequency, as you see on the plot of the right. That bright red region there is almost 100% efficient. Now let's put all these ideas together in one complex figure. Okay, and there's a lot here, but just start by looking at the left. On the left here, you can see in orange is the Sabatier volcano, the Sabatier peak concept we started with. So you can see it goes up to the peak maximum there in red and then comes back down here in orange. You can see that if I was to oscillate a catalyst, I would move between about 0.5 and 1.5. And if I oscillated fast enough, I would be up here at the resonant frequency that I talked about earlier. All right, now let's compare the plot on the left to the plot on the right. On the plot on the right now, I'm plotting the applied frequency versus the average turnover frequency, just like I was showing earlier. So as I said before, if you start at low frequencies here, you end up with a very low reaction rate below the Sabatier peak. And as I increase the frequency, I eventually surpass the Sabatier peak and go all the way up to this resonance frequency right there. At that point, if I increase the applied frequency anymore, I'm not going to increase the rate of reaction. Now, what I can do is I can plot the turnover frequency of the catalyst multiplied by its turnover efficiency, and that gives me my effective rate. And you can see here in pink, the peak associated with the resonance frequency matches only that particular condition, because only that particular condition has the amplitude that matches the inverted volcano you see over here on the left. And that's a simple way to think about what's happening in these particular systems. I think this figure puts everything together. All right, now I want you to think even bigger about what we're looking at. So we have a device here in the middle that lets us manipulate a surface. I can put in any signal that I want. I've shown you very simple ideas so far, like a sinusoidal wave, but I can start thinking of more complexity. Surface reactions are very complex. And so what could I input to change things like the rate, the selectivity, or the conversion? And this is what we've been developing over the past 5 years in this concept of catalytic resonance theory, of how we relate input frequencies to output performance of catalysts. Let me show you one more idea here to end this talk of what we can do with this to kind of get you thinking about it. A lot of these reactions are equilibrium controlled. For example, ammonia synthesis, water gas shift reaction, or dry methane reforming. If I change the temperature, I change the equilibrium. And this is problematic in the sense of process design, because I have to pick a temperature that's favorable for a reaction. Now, let me back up. If I think about a simulation of a very simple A to B reaction, I'm going to show you a simulation here that's very interesting. I can take this simulation and start with any composition that I want. So I could start with pure component B in a batch reactor. That's up here at the top left. I could start with pure A at the bottom left. And I can let this reaction to proceed over a long time, up to 1,000 seconds. And what you can see is that the equilibrium is plotted there as a dashed line. And the steady state is actually, the limit cycle is what the reaction goes to. So this is very strange. It's a catalytic reaction where the catalyst is oscillating in electronic state at a given frequency and about 0.2 electron volts at 1,000 hertz. And the reaction actually proceeds to 70% mole fraction of B rather than equilibrium 40%. Now this feels very wrong because we are always told that catalytic reactions go to equilibrium, and that is absolutely true for a static material. So if at about 200 seconds I turn off the dynamics, you can see that that's the vertical dashed line there. The reaction proceeds back to equilibrium. So we're not violating thermodynamics like this. We're just finding another way to put energy into a system. Now, the implications for this are enormous because it means that I can drive a reaction to a new composition that's not equilibrium. And that changes how I can think about processes. Now, why is this possible? Now, this is an idea that's been around for a very long time in biology, but we just haven't thought about it in catalysis because we haven't had the ability to modulate a surface with time. if my catalyst surface energy is changing with time, it becomes possible to apply a bias of a reaction forward or backward from equilibrium. This has been talked about by many people before, described it for particularly for proteins, and there's a book here on Life's Ratchet and many other source material that describe. But what you can see if you look on the left, where green molecules turn into yellow in that reaction as the energy moves up and down, in the strong binding state, it's very easy for green to flip to yellow. But then in the weak binding state, it's very difficult for yellow to go back to green, and it's not going to do it. We call this an energy ratchet, and it exists in many forms. This is a positive scaling ratchet. Over here on the right, this is a negative scaling ratchet. And this is how you can actually input energy into a catalytic reaction to drive it away from equilibrium. Now, can you drive a reaction forward and backward? The answer to that is very simply is if you look at a simulation, yes. So what you're looking at here is a simulation where we change the frequency we apply to that catalyst. And on the independent axis down here on the bottom is where the oscillation starts and ends. And what you can see very simply here is red means a forward reaction, blue means a backwards reaction, and green is equilibrium. So if you apply a sufficiently fast frequency to a catalyst, you can drive it forward or backward. And if you apply different voltages, starting and ending voltages, you can drive the reaction forward or backward. Most recently, we've defined an equation here that lets you predict whether the reaction is driven forwards or backwards. You can see that there in the lambda value on the right. All right, so let me end here by just pointing out why this matters so much to us. If we think of a reaction such as ammonia synthesis as a process is driven by the conditions of the reactor, which is dictated by what you can achieve with the catalyst. Because the catalyst is relatively slow, you have to operate at very high temperatures conventionally. And you have to also operate at very high pressures at that temperature because thermodynamics are not very favorable. If we do an alternative system where we use a ruthenium catalyst and we were to oscillate its electronic characteristics with time, this is a paper we published 2 years ago, you can look at it this way. Here's a simulation. So we start up the simulation on a static catalyst and it goes to equilibrium here at about 50% conversion at these conditions. Excuse me. And then we apply different frequencies of oscillation. At 5,000 hertz, it goes up significantly in conversion. As we decrease the frequency, the conversion decreases, and eventually it actually goes backwards from equilibrium. At 350 hertz, it's going less than equilibrium conversion. And if we turn off these dynamics, the reaction goes back to equilibrium. Now, there's a complexity here because this reaction has many, many steps, much more complex than the A to B reaction I was talking about earlier. So what's happening here is what we're trying to understand. What drives a reaction forward or backwards in a complex network like this? Let me give you another example. This is the oxygen evolution reaction. We just published this paper in ACS Energy Letters. And in this case, this is a very important, the key reaction in making hydrogen from water by electrolysis. We have water, we're going to break apart water and form oxygen as our product, and then the protons will go on to form hydrogen. In this case, this has a very famous overpotential volcano you can see right here. So as we change the catalyst descriptor, different metal oxides, we're going to show up at different conditions of overpotential needed to meet our target rate of 10 milliamps per square centimeter. This is a very famous volcano because iridium oxide sits up here at the top. Okay. Now, if I convert this to a rate volcano down here on the bottom, you can see here the vertical axis is my catalytic rate. And again, down here, this is my oscillation condition. You can see here are my static volcanoes at 2 different overpotentials. And if I oscillate the catalytic characteristics electronically with time, I can achieve catalytic rates that are significantly higher than the Sabatier peak. Now, I can accelerate the reaction or I can achieve the same reaction rate and lower the overpotential, as you can see right here. You can significantly lower the overpotential by putting energy into the surface by dynamics. So this could provide a way to give us faster catalysts or to use materials alternative to iridium oxide. So let me end here with the presentation. I want to give you a sense of what programmable chemistry and catalysis is. We have the ability to combine chemistry and materials together with perturbation to optimize systems for faster rates, better selectivity, or better conversion for a particular thermodynamic condition. What I like so much about this is the strategy. I don't have to come up with some particular material. I have to think about how I'm going to take a material that we might already have and modulate it with time to give me really great performance. What's exciting to me is that this goes after some of the massive targets we care about to address climate change. So hydrogen production, methanol synthesis, ammonia synthesis, alkane dehydrogenation, epoxidation, selective oxidation. There's so much work to do here that I think we're all working quite hard. And by we, I mean the U.S. Department of Energy has funded a research center, the Center for Programmable Energy Catalysis. This is headquartered at Minnesota, but you can see we have a team of researchers from all over the country at MIT, University of Michigan, University of Houston, UC Santa Barbara, and Ohio State University, all working together to build these devices to study dynamics, understand the computation, the chemistry, and the materials. So thank you for the opportunity to present to you today. I'm very grateful to speak to so many of you.